How many oceans are there on Earth? If you went to school before 2021, the answer was 4. The Atlantic, the Pacific, the Indian, and the Arctic. 4 oceans. That was the number. It was on every map, in every textbook, on every globe, sitting on every teacher's desk in every classroom in the world. 4 oceans. Simple, clean, settled science. Except it wasn't settled at all, because surrounding an entire continent at the bottom of the world, stretching across 20 million square kilometers of the most violent, most productive and least understood water on the planet, there was a 5th ocean, and for nearly a century we refused to put it on the map. Not because we didn't know it was there. We knew. Scientists had been studying it for generations. Sailors had been drowning in it for centuries. The water was different, the currents were different, the temperature was different, the life inside it was different. Everything about it screamed that this was its own distinct body of water, separate from the oceans it touched, defined not by the land around it but by the invisible river of cold water that circled it like a wall, and we just didn't count it. The story of the Southern Ocean, also called the Antarctic Ocean, is one of the strangest chapters in the history of how we draw the world. It is a story about politics, about stubbornness, about the limits of human categories, and ultimately about what happens when you ignore the biggest engine on the planet for so long that it starts to break down while you aren't paying attention. Let's go back to the beginning. When James Cook sailed into the southern latitudes in the 1770s, he knew the water was different. The seas below, about 60 degrees south, were colder, rougher and wilder than anything he had encountered. He didn't have the instruments to measure what was happening beneath the surface, but he could feel it. Every sailor who ventured that far south could feel it. There was a boundary down there, a threshold where the ocean changed its personality entirely. For the next 2 centuries, mapmakers argued about what to do with that boundary. Some called it the Southern Ocean. Some called it the Antarctic Ocean. Some called it the Austral Ocean. And some just lumped it in with whichever ocean happened to be nearby. The water south of Africa? That was the Indian Ocean. The water south of South America? That was the Pacific. The water south of Australia? Also the Pacific, or maybe the Indian, depending on who you asked. In 1937, the International Hydrographic Organization, the global body responsible for naming and defining ocean boundaries, finally recognized the Southern Ocean as its own distinct entity. It was official. 5 oceans. The map was updated. And then 16 years later, they took it back. In 1953, the WHO reversed the decision. The member countries couldn't agree on where the boundaries should be drawn. Unlike the Atlantic or the Pacific, the Southern Ocean doesn't have continents neatly fencing it in on all sides. It bleeds into the other 3 oceans. And because the political arguments about where exactly one ocean ends and another begins proved too messy to resolve, the IHO decided it was easier to just pretend the 5th ocean didn't exist. So from 1953 until 2021, the official answer to how many oceans are there was 4, even though every oceanographer in the world knew it should be 5. Think about that for a second. We had satellites that could photograph the entire planet. We had submarines that could dive to the deepest trenches. We had climate models running on supercomputers. And we couldn't agree that the body of water surrounding an entire continent was its own ocean. The United States Board on Geographic Names broke ranks in 1999 and started using the term Southern Ocean officially. No AA followed in February of 2021. And then on June 8th, 2021, World Oceans Day, National Geographic made the announcement that finally settled it for the public. They updated their maps. 5 oceans. The Southern Ocean was real. It was distinct, and it was going on every globe from that point forward. But what makes it different? What separates the Southern Ocean from the water just north of it? The answer is not a continent. It is a current. About 34 million years ago, Antarctica was still connected to South America. The 2 land masses were joined by a bridge of rock and ice that kept the southern waters contained, mixed up with the warmer currents flowing down from the tropics, but then the continents drifted apart. A gap opened up, and once that gap was wide enough, something extraordinary happened. Water began to flow through it, cold, dense water, driven by the relentless westerly winds that blow across the southern latitudes. And because there was no land to block it, this water kept going. It flowed east. It circled Antarctica. It connected with itself on the other side, and it never stopped. This is the Antarctic circumpolar current, and there is nothing else like it on Earth. It is the largest ocean current in existence. It carries roughly 150 times the volume of all the world's rivers combined. It flows from west to east in a continuous loop around the entire continent, reaching from the surface of the ocean all the way down to the seafloor thousands of meters deep. At its widest, it stretches nearly 2,000 kilometers across. It is not just a current. It is a wall, a boundary, a moat of cold water that isolates Antarctica from the warmth of the rest of the world. The ACC, as scientists call it, is the reason Antarctica has its massive ice sheet. Before the current formed, Antarctica was warmer. It had forests, it had rivers, but once the circumpolar current sealed off the continent, the warm tropical water could no longer reach it. Antarctica froze, and it has stayed frozen ever since, locked behind a spinning ring of cold water that keeps the heat out. But the ACC does far more than just keep Antarctica cold. It is the connecting thread between every major ocean basin on the planet. The Atlantic, the Pacific, and the Indian Oceans all feed into the ACC and draw from it. Heat, salt, nutrients, carbon dioxide, oxygen. All of these things are exchanged through the circumpolar current. It is the post office of the global ocean, the highway system, the circulatory network. Without it, the oceans would be isolated pools. With it, they form a single interconnected system that regulates the climate of the entire Earth. And the water inside the ACC is different from the water just outside it. Inside the ring, the ocean is colder and slightly less salty than the subtropical water to the north. This creates a sharp ecological boundary. Species that live inside the Southern Ocean often live nowhere else. Emperor penguins, Weddell seals, Antarctic krill, those tiny shrimp-like creatures that form the foundation of one of the most productive food webs on the planet. The phytoplankton blooms that erupt when the sea ice melts in spring are so massive they can be seen from space. Great milky green clouds spreading across the surface, pulling carbon out of the atmosphere and feeding everything from krill to whales. This is a distinct ecosystem, a distinct body of water, a distinct ocean. And for 68 years we left it off the map. Now you might think that the naming debate was just a formality, a bureaucratic squabble with no real consequences. But recognition matters. When the Southern Ocean wasn't on the map, it wasn't in the conversation. Students didn't learn about it. Policymakers didn't prioritise it. Conservation efforts struggled because the water they were trying to protect officially belonged to 3 different oceans, each governed by different treaties and different rules. As of right now, only about 13% of the Southern Ocean is protected. The Ross Sea Marine Protected Area, established in 2016, is the world's largest, but it covers just a fraction of the total area. Industrial fishing for krill and Patagonian toothfish, which restaurants sell to you as Chilean sea bass, has been hammering this ecosystem for decades, and climate change is hitting the Southern Ocean harder and faster than almost anywhere else on the planet. The Commission for the Conservation of Antarctic Marine Living Resources has 4 more marine protected area proposals under consideration right now. If all 4 were adopted, the protected area would climb to about 26%. That is still not enough, but it would be a start. Recognition also matters for science. When you study the Southern Ocean as an extension of the Pacific, you miss the patterns that only become visible when you look at it as its own system. The circulation dynamics, the carbon uptake, the ice formation, the deep water production, All of these processes are unique to the Southern Ocean, and understanding them requires treating this body of water as what it is, not the bottom of 3 other oceans, but an ocean in its own right. Seth Sikora Bodhi, a NOAA marine scientist, said it best when describing what it feels like to be there. Anyone who has visited the Southern Ocean struggles to explain what makes it so different, but they all agree on one thing. The glaciers are bluer, the air is colder, the mountains are more intimidating, the landscapes are more captivating than anywhere else you can go. It is a world apart, and it always has been. We just took a very long time to admit it, but the naming debate, as important as it was, turned out to be the least of our mistakes, because while we were arguing about what to call this ocean, the ocean itself was changing, and the changes it was undergoing would turn out to be some of the most consequential shifts in the modern history of the planet. We thought we understood how the Southern Ocean worked. We thought the current would keep flowing, the water would keep sinking, the carbon would keep getting buried, and the ice would keep forming. We had models, we had equations, we had a story that made sense, and the Southern Ocean was about to tear that story apart. To understand how, you first need to understand what this ocean actually does for the rest of the world, because the Southern Ocean isn't just different, it is essential. It is the engine that drives the climate of the entire planet. And that engine, the one we ignored for nearly a century, the one we couldn't even agree to name, it is the one that is starting to break down. So let's talk about what the Southern Ocean actually does. Let's talk about the machine at the bottom of the world, the one that moves heat, buries carbon, creates the densest water on the planet, and feeds oxygen into every ocean basin. The one that has been running for 34 million years without a service check. Because once you understand how it works, you will understand why the fact that it is changing should keep every climate scientist on Earth awake at night. Imagine you are standing in a room with 3 doors. Behind each door is a different ocean, the Atlantic, the Pacific, the Indian. Each one is massive, ancient, and filled with its own currents and ecosystems. Now imagine that underneath the floor, connecting all 3 rooms, there is a river. A cold, dark, heavy river that flows through the foundations of the entire building, carrying heat from one room to another, pulling carbon dioxide out of the air and dragging it down into the basement, delivering oxygen to places that would otherwise suffocate. That river is the Southern Ocean, and the building is the planet. The way it works is deceptively simple. Warm water from the tropics drifts south toward Antarctica. As it gets closer to the pole, it cools. The westerly winds that scream across the open water push the surface layer northward, and colder water from below rises up to replace it. This upwelling brings ancient water from the deep ocean back to the surface, water that has been circulating in the abyss for centuries, carrying nutrients and dissolved gases that accumulated during its long journey through the dark. When this deep water reaches the surface near Antarctica, it does 2 things. First, it absorbs carbon dioxide from the atmosphere. The cold water is like a sponge for CO2. It soaks it up. Second, it absorbs heat. The sun warms the surface and the ocean drinks it in. Then the water cools further, gets denser, and begins to sink. Some of it sinks to intermediate depths and flows north as what scientists call Antarctic intermediate water. This water can travel all the way to the temperate latitudes of the northern hemisphere, carrying the carbon it absorbed with it, burying it in the interior of the ocean, where it can stay locked away for hundreds of years. But some of the water goes even deeper, much deeper, along the edges of the Antarctic continent, particularly in the Weddell Sea and the Ross Sea. Something remarkable happens every winter. Sea ice forms on the surface. When seawater freezes, it doesn't trap the salt. The salt gets expelled into the surrounding water, a process called brine rejection. This makes the water underneath the ice saltier and denser. At the same time, fierce winds blowing off the continent cool this water to temperatures just above freezing. The result is the densest, heaviest water in the entire ocean. This water is called Antarctic bottom water, and it is the lifeblood of the deep sea. Once formed, Antarctic bottom water sinks. It plunges off the continental shelf and pours into the abyss like a slow-motion waterfall. It flows along the ocean floor, creeping northward through the deep basins of the Atlantic, the Pacific and the Indian Oceans. It fills the bottom of the world. By volume, Antarctic bottom water makes up somewhere between 30 and 40% of the entire global ocean. Nearly half of all the water in the sea was born here, in the freezing darkness off the coast of Antarctica. And it carries gifts. Oxygen, for one. The cold water at the surface absorbs oxygen from the atmosphere before it sinks. As it spreads through the deep ocean, it delivers that oxygen to the abyss, keeping the deep sea habitable for the creatures that live there. Without this constant supply of oxygenated water, the deep ocean would become a dead zone, stagnant, anoxic, lifeless. It also carries heat, or rather, it redistributes it. The entire process of warm water flowing south, cooling, sinking and spreading north is part of what scientists call the global thermohaline circulation, sometimes called the Great Ocean Conveyor Belt. It is the mechanism by which the planet distributes heat from the tropics toward the poles and back again, a slow, relentless balancing act that has been running for millions of years. The numbers involved are staggering. The Antarctic circumpolar current alone moves about 150 million cubic meters of water per second. That is 150 times the combined flow of every river on Earth. It reaches from the surface to the seafloor, thousands of meters deep. It connects all three major ocean basins, making it the only truly global current in existence. A study published in Nature in 2024, led by researchers from Columbia University's Lamont Doherty Earth Observatory, used sediment cores drilled from the ocean floor in the far southeast Pacific to reconstruct the behavior of the ACC over the last 5.3 million years. What they found was both illuminating and deeply unsettling. During past natural climate swings, the current moved in tandem with Earth's temperature. When the planet warmed, the ACC sped up. When it cooled, the current slowed down, and the periods when the current was running fastest consistently corresponded with times when Antarctica's ice sheets were retreating. The warm water was getting in, the ice was pulling back, and the current was the gateway. This is not just history. The ACC has been speeding up in recent decades, driven by strengthening westerly winds linked to human-caused climate change. If the pattern of the last 5.3 million years holds, and there is no reason to think it won't, this speed-up will continue as global warming proceeds. More warm water reaching Antarctica, more ice melting, more meltwater pouring into the Southern Ocean, disrupting the very processes that keep the conveyor belt running. But before we get to the disruption, let's talk about the other job the Southern Ocean does, the one that might matter even more than a heat distribution. Carbon. The Southern Ocean is the single most important carbon sink on the planet. It absorbs roughly 40% of all the CO2 that enters the ocean from human activity. Think about that. Nearly half of the carbon dioxide the ocean swallows passes through these waters. It does this through two mechanisms, and both of them are remarkable. The first is the physical pump. Cold water at the surface absorbs CO2 from the atmosphere. That water sinks and carries the dissolved carbon into the deep ocean, where it can remain sequestered for hundreds to thousands of years. The colder the water, the more CO2 it can hold, because cold water has a higher capacity for dissolved gases than warm water. The Southern Ocean is very, very cold, so it absorbs a disproportionate share of the planet's excess carbon. The second is the biological pump. Every spring, when the sea ice retreats and sunlight floods the surface, enormous blooms of phytoplankton erupt across the Southern Ocean. These tiny organisms photosynthesize, pulling carbon from the water and converting it into organic matter. When they die, they sink. Their tiny bodies drift down through the water column, carrying the carbon they absorb with them into the deep. This biological rain of dead phytoplankton, fecal pellets and marine snow is estimated to remove about 3.5 million tons of carbon from the ocean each year. That is equivalent to roughly 12.8 million tons of CO2 removed from the system. And the nutrients that fuel these blooms? They come from the upwelling water. The deep ancient water that rises to the surface in the Southern Ocean is rich in iron, nitrogen and phosphorus. The nutrients that accumulated during centuries in the abyss get delivered to the sunlit surface, where they feed the phytoplankton, which feed the krill, which feed the fish, which feed the seals and penguins and whales. The Southern Ocean isn't just a carbon sink. It is the foundation of one of the most productive ecosystems on Earth. There is one more thing the Southern Ocean does that rarely gets the attention it deserves. It stores heat. An almost incomprehensible amount of heat. Since the Industrial Revolution, human activity has pumped enough greenhouse gases into the atmosphere to trap an enormous surplus of energy. More than 90% of that excess heat has been absorbed by the ocean. And of all the ocean's heat uptake, the Southern Ocean accounts for roughly 80%. 80%. This single body of water, the one we couldn't even agree to name until 4 years ago, is absorbing the vast majority of the heat that would otherwise be cooking the atmosphere. Part of the reason is geography. The Southern Hemisphere atmosphere is cleaner than the Northern Hemisphere. There are fewer factories, fewer cargo ships, fewer sources of the aerosol pollution that actually reflects sunlight and provides a slight cooling effect. Without that reflective shield, more solar energy reaches the ocean's surface in the south. The Southern Ocean also has a uniquely efficient mechanism for pulling heat from the surface into the deep. The overturning circulation takes warm surface water, cools it, and pumps it down into the abyss, effectively storing the heat in the ocean's interior where it can't warm the atmosphere. For decades this has been a gift. The Southern Ocean has been absorbing our mess, quietly soaking up the heat and the carbon that would otherwise be making climate change even worse than it already is. It has been the planet's buffer, its safety valve, its shock absorber. But there is a problem with shock absorbers. Eventually they wear out. The system that has been protecting us depends on a delicate balance. Cold water has to sink. The circulation has to keep turning. The ice has to keep forming. The nutrients have to keep upwelling. If any part of this machine breaks down, the consequences ripple outward, through every ocean, every continent, every weather system on the planet. And right now, in real time, the machine is breaking down. The water that is supposed to sink isn't sinking the way it used to. The circulation is slowing. The ice is behaving in ways nobody predicted. And the consequences are already showing up in places thousands of miles from Antarctica. The engine at the bottom of the world, the one that connects every ocean, buries our carbon, distributes our heat, and oxygenates the deep sea, is misfiring. And the first sign that something was seriously wrong came from the water itself. To understand what is going wrong, you need to picture the process of Antarctic bottom, water formation one more time. Freezing cold winds blow off the Antarctic continent. Sea ice forms on the surface of the Weddell Sea. Salt gets expelled from the ice into the water below. The water becomes denser, heavier, and it sinks. It plunges off the continental shelf and fills the abyss. This has been happening every winter, without interruption, for millions of years. The water sinks, it spreads, it carries oxygen and cold and carbon into the deepest parts of every ocean basin. Then centuries later, it rises again somewhere else and the cycle continues. But over the last few decades, something has changed. The water is not sinking the way it used to. In 2023, a landmark paper published in Nature made a statement that stunned the oceanographic community. The abyssal overturning circulation in the Southern Ocean, the mechanism responsible for forming and exporting Antarctic bottom water, was slowing down dramatically. The researchers estimated that if current trends continued, the formation of bottom water could decline by more than 40% by 2050. Not in some distant future, not in the next century, by 2050, within the lifetime of most people alive today. The reason is meltwater. As the Antarctic ice sheet loses mass, enormous volumes of fresh water are pouring into the ocean around the continent. This meltwater is lighter than the cold, salty water that is supposed to sink. When you dump fresh water on top of the ocean surface around Antarctica, it acts like a cap. It sits on top. It prevents the dense water from forming properly. And if the dense water does not form, it does not sink. And if it does not sink, the entire conveyor belt slows down. The Weddell Sea, one of the two primary factories for Antarctic bottom water, has been hit especially hard. Research published in Nature Climate Change showed that the volume of Weddell Sea bottom water had dropped by 30% since 1992. 30% of the densest water in the Weddell Sea gone, not gradually over thousands of years, in 3 decades, and it gets worse. NOAA's Climate Programme Office reported that the northward transport of Antarctic bottom water across the global ocean had declined by roughly 12% between 2000 and 2020. This means that the deep ocean is receiving less oxygenated, cold water than it has in modern history. The bottom of the Atlantic is getting warmer. The bottom of the Pacific is getting warmer. The oxygen supply to the deep sea is diminishing. If you are thinking that this sounds like a very slow, very abstract problem that won't affect anyone in any real way, let me be direct with you. This is one of the most dangerous developments in modern climate science. When the overturning circulation slows down, several things happen simultaneously, and none of them are good. First, the deep ocean begins to lose oxygen. Antarctic bottom water is the primary delivery system for oxygen to the abyssal plains. Without that supply, the deep ocean starts to suffocate. This is not hypothetical. Observations from deep-sea monitoring stations have already detected declining oxygen levels in several deep ocean basins. The creatures that live in the abyss, the strange and ancient organisms that depend on this oxygen, face an existential threat that most of the world has not even begun to consider. Second, the carbon that the Southern Ocean has been burying starts to come back. When the overturning circulation is running properly, carbon absorbed at the surface gets dragged into the deep and locked away for centuries. But when the circulation slows down, less carbon gets buried. And worse, the carbon that was already stored in the deep ocean may start to rise back toward the surface as the water stagnates and the pressure changes. Third, and this is the one that should worry everyone, the heat stays at the surface. Normally, the overturning circulation is like an elevator that takes heat from the surface and carries it into the deep ocean, away from the atmosphere. When the elevator stops working, the heat has nowhere to go. It stays in the upper ocean. It stays in the atmosphere. It accelerates surface warming. It melts more ice, which dumps more fresh water into the ocean, which slows the circulation further, which traps more heat at the surface. This is a feedback loop, and it is already running. But in early 2025, a study published in the Proceedings of the National Academy of Sciences revealed something that went beyond a simple slowdown. The researchers found evidence that a portion of the Southern Ocean's overturning circulation had actually reversed. Let that word land for a moment. Reversed. In the normal system, cold dense water sinks at the surface and flows into the deep ocean. In the reverse system, deep water is rising. Water that has been stored in the abyss for centuries, water that is loaded with heat and dissolved carbon, is coming back up to the surface. The study focused on the southern meridional overturning circulation and found that in certain regions, the flow had flipped direction. Instead of surface water sinking to feed the deep ocean, deep water was welling up into the upper ocean. The implications of this are almost too large to summarize in a single sentence, but here is the attempt. The Southern Ocean is not just failing to absorb our excess heat and carbon. In some areas it has started releasing the heat and carbon it already stored. Surface salinity in the Southern Ocean has been increasing since around 2016. This is consistent with reduced freshwater input from below and increased evaporation at the surface, but it also points to fundamental changes in how water masses are mixing and interacting. The normal layering of the ocean, cold fresh water at the bottom, warmer saltier water above, is being disrupted. The boundaries between water masses are blurring. Think of it this way. For millions of years, the Southern Ocean has been operating like a giant battery. It absorbs heat and carbon at the surface, stores them in the deep ocean, and keeps them locked away. The battery has been charging decade after decade, absorbing more and more of the excess energy that human civilization has been pumping into the atmosphere. But a battery can only hold so much charge, and when you start to overload it, strange things happen. The chemistry changes, the structure weakens, and eventually the battery starts to discharge whether you want it to or not. The Southern Ocean is not just a passive sink anymore. It is becoming an active participant in climate change, amplifying the very problem it was supposed to buffer. And the scariest part? The models did not predict this would happen this fast. The 2023 Nature paper that first flagged the abyssal slowdown was projecting 40% decline by 2050. But the 2025 PNAS paper showing actual reversal suggests that the timeline is accelerating. The system is moving faster than the models predicted. The models were built on the assumption that the Southern Ocean would continue to absorb heat and carbon at roughly historical rates for decades to come. That assumption is failing. What happens next depends on how the rest of the ocean system responds. If the overturning circulation continues to weaken, the deep ocean will warm. Oxygen levels in the abyss will drop. Carbon, that has been locked away for centuries, will begin to return to the atmosphere. Sea level will rise faster as the thermal expansion of warming deep water adds to the meltwater contribution from glaciers. And there is a mechanism, one that climate scientists have been quietly worrying about for years, that ties all of these changes together into something even more alarming. It involves what happens when you try to fix the problem, what happens when humanity actually succeeds in reducing emissions, when we reach net zero, when we start pulling carbon out of the atmosphere. Because the Southern Ocean has been storing so much heat for so long that even if we stop warming the planet, the ocean might not cooperate. There is a scenario in which the Southern Ocean, the great absorber, the planetary buffer, the engine at the bottom of the world, turns around and gives it all back. Scientists have a name for this scenario. They call it the thermal burp, and a study published in early 2025 suggests that it is not just possible, it may be inevitable. Picture a kettle on a stove. You turn the burner on. The water heats up from the bottom. The heat builds. But the water at the top of the kettle stays relatively cool for a while, because heat rises slowly through liquid. You can touch the top of the kettle and it feels warm but manageable. The real heat is building below, stored in the lower layers of water, accumulating energy that you cannot see from the outside. Now imagine you turn the burner off. You would expect the water to cool down, and the water at the top does cool. But the heat stored in the bottom of the kettle doesn't just disappear. It has to go somewhere, and eventually it rises. The deep heat works its way up to the surface, and for a while, even after the burner is off, the top of the kettle actually gets warmer. This is, in the most simplified terms, what the Southern Ocean may be about to do to the planet. In early 2025, researchers published a study in AGU Advances that modelled what would happen to the Southern Ocean under a very specific and very hopeful scenario. A scenario where humanity not only stops emitting greenhouse gases, but actually achieves net negative emissions, where we pull more carbon out of the atmosphere than we put in, where global temperatures begin to decline. You would think under that scenario the Southern Ocean would cool down along with everything else. You would think the great absorber would simply stop absorbing and let the planet heal. That is not what the model showed. Instead, the researchers found that when surface cooling begins, It triggers a change in the way the Southern Ocean circulates. The surface water cools and becomes denser. This reinvigorates the overturning circulation. The deep water, which has been sitting in the abyss accumulating heat for decades, gets pushed back toward the surface by the newly sinking cold water. And when that ancient warm water reaches the surface, it releases its stored heat into the atmosphere. The Southern Ocean burps, not a gentle, gradual release, an abrupt one. The model showed that the heat release happens in a non-linear fashion. It is not proportional to the cooling at the surface. Instead, there is a threshold, a tipping point, where the deep overturning suddenly strengthens and begins pumping warm water upward at a rate far faster than the slow, steady accumulation that put it there in the first place. The result is a period lasting decades to potentially a century, where the Southern Ocean actively warms the atmosphere even as the rest of the planet is trying to cool down. Global temperatures stop declining or even start rising again, not because humans are still emitting carbon, but because the ocean is releasing the heat it stored during the decades when we were. This is counterintuitive enough to feel like it can't be real, but the physics behind it are sound. The deep ocean has been absorbing excess heat for more than a century. That heat is real. It is stored in the water column, and the laws of thermodynamics say it has to go somewhere eventually. The question was never whether the heat would come back. The question was when and how fast. The AGU Advances study suggests the answer is sooner and faster than anyone expected. And here is the twist that makes this even more unsettling. The study found that while the heat comes back in a rush, the CO2 does not. The carbon that the Southern Ocean absorbs stays mostly locked in the deep water, even as the heat escapes. This is surprising because heat and carbon were absorbed together. You would expect them to be released together, but the chemistry of carbon dissolution in seawater is different from the physics of heat transfer. The carbon bonds with the water in ways that make it harder to release, while the heat simply rises with the warming water. So what does this mean in practical terms? It means that even under the best case scenario, even if we do everything right, even if we achieve the most ambitious climate goals ever set, the Southern Ocean will push back. It will release heat that was stored decades ago, sustaining surface warming for a generation or more after emissions stop. The climate will appear to resist our efforts. Temperatures will stay stubbornly high, or even rise temporarily, even as atmospheric CO2 declines. This does not mean that cutting emissions is pointless. Far from it. The carbon stays locked away, which is good. The atmosphere eventually recovers, which is good. But the recovery timeline is longer and messier than any politician has promised. There is no clean break. No moment where we flip a switch and the planet starts healing on schedule. The Southern Ocean has been absorbing our excess heat for so long that the payback period stretches across decades. And there is another layer to this. The thermal burp doesn't just warm the atmosphere. It warms the surface of the Southern Ocean itself, which could accelerate the melting of ice shelves around Antarctica, which could accelerate sea level rise, which could dump more fresh water into the ocean, which could disrupt the overturning circulation all over again, creating a cascading sequence of events where one feedback loop triggers another and the system oscillates in ways that no model can fully predict. The researchers were careful to note the uncertainties in their work. Models are simplifications of reality. The actual ocean is messier, more complex, more full of surprises than any simulation can capture. But the underlying mechanism, heat stored in the deep ocean, returning to the surface when circulation patterns shift, is robust. It is based on established physics, and the amount of heat stored in the Southern Ocean is not in dispute. It is enormous. Since 1970, the ocean as a whole has absorbed roughly 380 zettajoules of excess heat. To put that number in perspective, a single zettajoule is equivalent to the energy released by roughly 160 billion tons of TNT. The Southern Ocean has absorbed the lion's share. That energy is sitting in the water column right now, waiting. We were wrong about the Southern Ocean being a permanent solution to our heat problem. It was never permanent. It was always temporary storage, and the storage facility has started leaking. But the surprises from the Southern Ocean don't end with heat and circulation, because while scientists were discovering that the water was changing, that the currents were shifting, that the deep ocean was warming, and the circulation was reversing, something else happened. Something that had nothing to do with climate models or ocean temperatures. An iceberg, the size of a small country, broke off from the Antarctic coast. And when scientists sailed to the spot where it had been, they found a world that no one knew existed. A world that had been sealed under ice for thousands of years. And it was alive. The Southern Ocean is the least explored ocean on Earth. More people have been to space than have been to its deepest waters. The International Space Station orbits closer to the average person's daily life than most of the Southern Ocean seafloor is to the nearest research vessel. The conditions are brutal. Storms that rage for weeks, waves that reach the height of 5-story buildings, temperatures that can kill an unprotected human in minutes, ice that can crush a ship's hull like paper. For most of human history, what lived beneath the surface of the Southern Ocean was almost entirely a mystery. Scientists had done some sampling, some trawling, some camera drops, but the picture was fragmented. The prevailing assumption, based on the limited data available, was that the deep sea floor around Antarctica was relatively sparse, cold, dark, low in nutrients, and home to only the hardiest and simplest organisms, a biological desert at the bottom of the world. That assumption was spectacularly wrong. In January of 2025, a massive iceberg designated F-84 carved from the George VI ice shelf on the western side of the Antarctic peninsula. It was enormous, roughly 510 square kilometers, about the size of the Spanish island of Ibiza. When it broke free and drifted away, it exposed a section of seafloor that had been sealed under more than 150 meters of solid ice for thousands of years. No sunlight had reached this water in millennia. No surface nutrients had filtered down. By every traditional measure, this should have been one of the most barren places in the ocean. The Schmidt Ocean Institute's research vessel Falkor 2 was in the region, and they redirected to investigate the newly exposed seabed. What they found there was so unexpected, so vividly alive, that it rewrote what scientists thought they knew about life under Antarctic ice. The seafloor was covered with organisms, vibrant, diverse, abundant life, clinging to rocks and spreading across the sediment in every direction. Sea anemones waved gently in the current. Colonies of bryozoans, tiny filter-feeding animals that build intricate skeletal structures, covered the rocky surfaces. Sea spiders, those bizarre leggy creatures that look like something from science fiction, picked their way across the bottom. Icefish, translucent and ghostly, with antifreeze proteins in their blood that keep them alive in water cold enough to kill almost anything else, drifted through the scene. There were octopuses, there were worms, there were sponges and sea cucumbers and starfish. There were organisms that had clearly been thriving here for a very long time, building communities in total darkness, fed not by sunlight but by chemical processes and the slow rain of organic material from the water column above. This was not a desert, it was a garden. The previous scientific understanding of subice ecosystems was based on a handful of studies, some conducted decades ago, that found relatively impoverished communities under Antarctic ice shelves. Those studies had led to a general assumption that ice shelf environments were too isolated, too nutrient poor, and too cold to support significant biodiversity. The discovery under the George VI ice shelf didn't just contradict that assumption, it demolished it. And this was only the beginning. Later in 2025, a joint expedition by the UK's Necton Foundation and the Schmidt Ocean Institute conducted a major deep-sea survey in the Southern Ocean, exploring waters around the South Sandwich Islands and the South Orkney Islands. They used remotely operated vehicles to descend to depth that had never been surveyed, filming the seafloor with high-definition cameras and collecting specimens for analysis. In October of 2025, the team announced that they had confirmed at least 30 species entirely new to science from these waters, and the nature of these species was frankly astonishing. Among the discoveries was a carnivorous sponge, not a passive filter feeder sitting quietly on a rock, a predator. The species, classified within the genus Chondrocladia, was found at a depth of 3,601 meters. It grows tiny hooks on its surface, like biological Velcro, and uses them to snare small crustaceans and other animals that drift too close. Once caught, the prey is slowly enveloped and digested. The researchers informally described it as a death ball sponge, which is about as metal as a marine biology gets. There were zombie worms, belonging to the genus Osedax, creatures originally discovered in other oceans that bore into the bones of dead whales on the seafloor. They have no mouth, no stomach, no gut. Instead, they dissolve bone using acid secreted from their root-like tissues and rely on symbiotic bacteria to extract nutrients from the dissolved bone matter. Finding them in the Southern Ocean confirmed that whale falls, the sunken carcasses of dead whales that create temporary oases of life in the deep sea, are playing an important ecological role in Antarctic waters that was previously unrecognized. There were Elvis worms, a type of polychaete worm covered in shimmering iridescent scales that reflect light in ways reminiscent of a sequined jumpsuit. They are scavengers, feeding on whatever organic material they can find at the crushing depths where they live. And perhaps the most spectacular discovery of all came not from the seafloor, but from the water column itself. In 2025, a colossal squid was filmed in its natural habitat for the first time in history. This animal, one of the largest invertebrates on the planet, with eyes the size of dinner plates and rotating hooks on its tentacles, had only ever been studied from dead or dying specimens pulled up by fishing vessels. Nobody had ever seen one alive, moving, hunting, in the deep waters it calls home, until now. The expedition team estimated that they had only assessed about 30% of the biological samples they collected. 7 out of 10 specimens were still sitting in preservation fluid, waiting to be examined. The true count of new species from this single expedition is almost certainly far higher than 30, and this was just one expedition, covering a tiny fraction of the Southern Ocean's vast seafloor. The implication is staggering. We have barely scratched the surface of what lives in the Southern Ocean. The deep waters around Antarctica may harbour thousands of species that have never been described, never been photographed, never been named. An entire biosphere, hidden in the cold dark, evolved in isolation over millions of years while we argued about whether the ocean it lived in was even a real ocean. And here is what makes these discoveries urgent, rather than just fascinating. These ecosystems are changing. The warming of the deep ocean, the declining oxygen levels, the shifts in circulation, the retreat of ice shelves, all of the processes described earlier in this video are altering the environment that these creatures depend on. Species that evolved over millions of years in stable and cold, dark conditions are now facing rapid environmental change. The carnivorous sponge, at 3,601 meters, has likely never experienced water temperatures significantly different from what it knows. The ice fish with antifreeze proteins evolved specifically for sub-zero conditions. The communities under ice shelves that were only just discovered may be exposed to open water and light for the first time in millennia as those shelves collapse. We are simultaneously discovering these organisms and threatening them. We are arriving just in time to watch what might be the beginning of their decline. The race is on. Scientists are trying to document and understand the biodiversity of the Southern Ocean before it changes beyond recognition. The Ocean Census Initiative, launched in partnership with the Nippon Foundation, has set a goal of discovering 100,000 new marine species over the next decade, and the Southern Ocean is one of its priority targets. But the expeditions are expensive, the conditions are brutal, and the clock is ticking. Every iceberg that calves reveals a new world. And every year that passes changes that world a little more. But the discoveries beneath the ice are not the only surprises the Southern Ocean has delivered, because above the surface the ice itself has been doing something that nobody can fully explain, something that seems to contradict everything we think we know about climate change, and yet, paradoxically, confirms that the Southern Ocean is undergoing changes far more complex than any simple warming story can capture. The ice is doing something impossible. It is growing and shrinking at the same time. And the explanation for how that can be true involves an underwater mountain, a hole in the ice the size of a country, and a mystery that took scientists nearly 50 years to solve. In the 1970s, satellites were just beginning to give humanity its first real view of the Antarctic sea ice, and almost immediately they spotted something that should not have been there. In the middle of the Weddell Sea, one of the coldest, most ice-covered stretches of ocean on Earth, there was a hole, not a small gap where the wind had pushed ice floes apart, a massive opening in the sea ice, roughly the size of New Zealand, where the ocean surface was exposed to the atmosphere in the dead of Antarctic winter. Where there should have been an unbroken sheet of frozen white, there was dark open water. Scientists call this kind of feature a polynya. Polynyas are not entirely unusual near the coast, where winds can push ice away from the shore. But this one was in the open ocean, hundreds of kilometres from any coast, sitting above a submerged topographic feature called the Maud Rise, an underwater mountain that rises from the abyssal plain to within about 1,700 metres of the surface. The Maud Rise polynya appeared in 3 consecutive winters, from 1974 to 1976. Then it vanished. The sea ice closed back over, and for the next 40 years it did not come back. Scientists debated its cause. Theories range from volcanic heat underneath the seamount to unusual storm patterns to deep ocean mixing triggered by unknown processes, but without a recurrence, the mystery remained unsolved. Then, in 2017, it came back. A large polynya opened again over the Maud Rise, this time observed by a new generation of satellites with far better resolution and instrumentation. It was smaller than the 1970s version, but still enormous, roughly 50,000 square kilometres of open water where ice should have been. And this time scientists had the tools to figure out what was happening. A study published in Science Advances in 2024 finally cracked the case. And the answer turned out to be a beautiful piece of oceanographic detective work. Here is what happens. The Maud Rise sits on the seafloor like a giant bump. When ocean currents flow over and around this bump, they create disturbances in the water column, much like a rock in a river creates eddies and turbulence downstream. One of the effects of this disturbance is something called Ekman transport, a process where the interaction between wind, the Earth's rotation, and the ocean currents causes water to spiral and move laterally. In the case of the Maud Rise, the Ekman transport pushes saltier, warmer water from below onto the flanks and top of the seamount. This salty water is denser than the fresher surface water above it. When enough of this salty water accumulates over the rise, the water column becomes unstable. The heavy salt water sitting below the light fresh water creates an inverted density structure that wants to flip. And when winter cooling makes the surface water cold and heavy enough, the whole column overturns. Deep warm water rushes to the surface. Surface water plunges downward. When that warm deep water hits the surface in the middle of winter, it melts the sea ice from below. The polynya opens, and it stays open as long as the mixing continues, because the warm water keeps reaching the surface and preventing the ice from refreezing. The 2024 study showed that the salt build-up happens over a cycle of several years. Salt slowly accumulates on the Maud Rise. The water column becomes progressively more unstable, and then when conditions align, the system flips and the polynya erupts. After a few seasons, the salt is flushed away. The water column restabilizes, and the ice reforms. Then the cycle begins again. This explained both the 1970s polynyas and the 2017 recurrence, and it also raised a troubling question. As the Southern Ocean warms and its salinity patterns shift, will these overturning events become more frequent, more intense? Will the Maud Rise Polynya become a permanent feature of the Weddell Sea? Because every time the Polynya opens, it releases heat from the deep ocean into the atmosphere. It is essentially a vent, a release valve, where the stored energy of the abyss escapes directly into the air. And if climate change makes these venting events more common, it creates yet another feedback loop where warming leads to more heat release, which leads to more warming. But the Maud Rise Polynya, as dramatic as it is, only tells part of the ice story. Because while open ocean polynyas have been appearing and disappearing in cycles, the broader picture of Antarctic ice has been doing something that seems to make no sense at all. In 2023, Antarctic sea ice hit its lowest extent on record. The ice that forms on the ocean surface around Antarctica each winter, which normally expands to cover millions of square kilometres, failed to grow to anywhere near its historical average. The deficit was extraordinary. Scientists called it unprecedented. In the years since 2015, the Southern Ocean has lost an area of sea ice roughly equivalent to the size of Greenland. Just gone. Not there anymore. You would expect this. The planet is warming, the ocean is warming. Of course the sea ice is shrinking. Climate change 101. But then, in the midst of this decline, NASA published data showing something that appeared to contradict the entire narrative. Between 2021 and 2023, the Antarctic ice sheet, the enormous mass of glacial ice sitting on top of the continent itself, gained about 119 billion tons of mass per year. Gained, not lost, gained. The ice sheet was growing while the sea ice was shrinking. How is that possible? The answer lies in precipitation. Antarctica is technically a desert. It receives very little snowfall in most years, but during the 2021 to 2023 period, an unusual pattern of atmospheric circulation delivered significantly more snow to the Antarctic interior than normal. This extra snowfall accumulated on top of the ice sheet faster than the edges were melting and carving into the ocean. The net result was a temporary mass gain, and it is important to stress the word temporary. This is not evidence that Antarctica is doing fine. This is not evidence that climate change is a hoax. This is evidence that the climate system is complicated, that short-term variability can temporarily mask long-term trends, and that the Southern Ocean and the Antarctic ice are part of an interconnected system that does not follow simple linear rules. The long-term trend is clear. Over the past several decades, Antarctica has been losing ice. The glaciers that flow off the continent are accelerating. The ice shelves that buttress those glaciers are thinning and cracking. The West Antarctic ice sheet, which contains enough frozen water to raise global sea levels by more than 5 meters if it all melted, is considered one of the most vulnerable ice masses on the planet. But the system does not decline in a straight line. It lurches, it oscillates, it takes 2 steps back and 1 step forward. And those forward steps, those temporary gains, can be deeply misleading if you don't understand the larger context. The sea ice loss since 2015 is real. The ice sheet mass gain from 2021 to 2023 is also real. Both things are true at the same time, and both are consistent with a Southern Ocean that is undergoing rapid, complex, non-linear change. This is what makes the Southern Ocean so difficult to study, so difficult to model, and so difficult to communicate to the public. It doesn't behave the way you expect. It doesn't follow the simple narrative of everything warming, everything melting, everything declining on a neat graph. The reality is messier. The ice grows in one place and shrinks in another. The ocean absorbs heat in one decade and releases it in the next. The currents speed up and slow down and sometimes reverse entirely. And all of these changes, the circulation slow down, the thermal burp scenario, the Polynya cycles, the ice paradox, they are not isolated events. They are symptoms of a single underlying reality. The Southern Ocean is a system under stress. Its equilibrium, The balance that has persisted for millions of years is being pushed past its limits. We were wrong about the ice. We were wrong about the water. We were wrong about how quickly this could change. And the evidence suggests that the changes are not just accelerating. They are approaching critical thresholds beyond which the system may not return to anything resembling its previous state. Scientists have a word for these thresholds. They call them tipping points. And the Southern Ocean, according to a major study published in 2025, may be approaching several of them simultaneously. In 2025, a major review paper was published in the journal Nature by a team led by Nerily Abram from the Australian National University. The paper examined the state of the Antarctic and Southern Ocean systems and reached a conclusion that was, by the cautious standards of academic science, extraordinary. Multiple components of the Antarctic system, the ice shelves, the ice sheet, the ocean circulation, the sea ice, the marine ecosystems, are undergoing changes that are faster, more widespread, and more interconnected than previously recognized. Several of these changes are approaching or have already crossed thresholds that could trigger abrupt, irreversible shifts. That is not the language of a fringe paper or a speculative model. That is the conclusion of one of the most comprehensive assessments of the Antarctic system ever published, appearing in what is arguably the most prestigious scientific journal in the world. Let's walk through what they found. Start with the ice shelves. These are the floating extensions of the ice sheet that jut out over the ocean around the edges of Antarctica. They act like doorstops. As long as the ice shelves are intact, they hold back the glaciers that flow off the continent and slow their progress toward the sea. Remove the ice shelf, and the glacier behind it accelerates, pouring ice into the ocean and raising sea levels. Between 1997 and 2021, 71 of the 162 ice shelves around Antarctica reduced in volume. Not all of them, not even a majority. But 71 is a lot, especially when you consider the total amount of meltwater involved. The cumulative loss was estimated at 7.5 trillion tons of meltwater. That water went into the Southern Ocean, adding to the fresh water cap that is slowing down the formation of Antarctic bottom water and disrupting the overturning circulation. And the ice shelves are not just melting from above, they are being eaten from below. Warm ocean water is reaching the undersides of the ice shelves through channels and cavities, attacking them from the bottom. Studies using satellite measurements and ocean sensors deployed beneath the ice have found that the underwater anchors of key ice shelves, the points where the ice meets the bedrock and grips the seafloor, are shrinking roughly twice as fast as they were 50 years ago. When those anchors weaken, the ice shelf loses its grip. It becomes less stable. It cracks. It breaks apart. This is what happened to the Larsen B ice shelf in 2002. An ice shelf the size of Rhode Island disintegrated in just 35 days. The glaciers behind it immediately accelerated, and the ice that had been held back for thousands of years began pouring into the ocean. The ice shelf that keeps scientists up at night is the one in front of the Thwaites Glacier in West Antarctica. Thwaites is sometimes called the Doomsday Glacier, which is dramatic but not inaccurate. The glacier is enormous, roughly the size of Florida, and it sits on bedrock that slopes downward away from the coast. This means that as the glacier retreats, the ice gets thicker and thicker, and the retreating front exposes more and more ice to warm ocean water. It is a geometry that accelerates collapse. The more it retreats, the faster it retreats. If Thwaites goes, it would raise global sea levels by about 65 centimetres on its own. But it wouldn't go alone. Thwaites acts as a buttress for the broader West Antarctic ice sheet. If Thwaites collapses, the glaciers behind it would follow, and the total sea level rise from the West Antarctic ice sheet could exceed 5 metres over the coming centuries. The Abram paper also highlighted a discovery that sounds like it comes from science fiction. Researchers have found 85 active subglacial lakes beneath the Antarctic ice sheet. These are lakes of liquid water, trapped under kilometres of ice. kept liquid by geothermal heat from the Earth's interior and the insulating pressure of the ice above. These lakes are connected by channels. Water flows between them, and when a subglacial lake drains, the water lubricates the base of the ice sheet, allowing it to slide faster toward the ocean. We did not know about most of these lakes until very recently. We still don't know how they interact with each other, how much water they contain, or how their drainage patterns might change as the ice sheet responds to warming. What we do know is that they are there, they are active, and they add another layer of unpredictability to the behaviour of the Antarctic ice. And then there are the ecosystems. The same ecosystems that are only just being discovered are already showing signs of stress. Emperor penguins are the icons of Antarctica. They breed on the sea ice, using it as a platform to raise their chicks during the harsh Antarctic winter. When sea ice fails to form, or forms too late, or breaks up too early, the breeding season fails. In 2022 and 2023, several emperor penguin colonies experienced unprecedented breeding failures linked to early sea ice breakup. Chicks that were too young to swim were lost when the ice disintegrated under them. A study projected that if sea ice continues to decline at current rates, emperor penguins could face functional extinction by the end of this century. Not because every penguin dies, but because the breeding success drops below the level needed to sustain the population. The colonies would shrink year after year until there aren't enough breeding pairs to maintain genetic diversity. Antarctic krill, the tiny crustaceans that form the foundation of the Southern Ocean food web, face their own crisis. Krill depend on sea ice. Their larvae feed on algae that grows on the underside of the ice. Less ice means less food for juvenile krill, and krill populations have already declined significantly in parts of the Southern Ocean over the past several decades. Because krill are the primary food source for baleen whales, penguins, seals, squid and fish, a crash in krill populations would cascade through the entire ecosystem. The consequences of these changes are not limited to Antarctica. The Southern Ocean is connected to everything, and what happens there reaches around the world. When Antarctic bottom water production declines, the deep Atlantic and Pacific lose oxygen. This affects fisheries thousands of miles from the Antarctic coast. When the overturning circulation weakens, the distribution of heat across the planet shifts, altering weather patterns, storm tracks and monsoon systems in the tropics and subtropics. When ice shelves collapse and glaciers accelerate, the meltwater contribution to sea level rise shows up on coastlines from Miami to Mumbai, from London to Lagos. One of the less intuitive consequences involves the east coast of the United States. The overturning circulation in the North Atlantic, often called the AMOC, is linked to the Southern Ocean's deep water production. When less Antarctic bottom water flows into the Atlantic, it can disrupt the AMOC, which in turn affects the Gulf Stream. A weakened Gulf Stream means that water piles up along the US East Coast, causing regional sea levels to rise even faster than the global average. Cities like New York, Boston, and Charleston are particularly vulnerable to this dynamic. European climate is also at risk. The AMOC brings warm water from the tropics to the North Atlantic, which is why Western Europe has a milder climate than you would expect for its latitude. London is farther north than most of Canada, but it doesn't get Canadian winters because the Atlantic circulation delivers heat. If that circulation weakens, and there is strong evidence that it already is, Europe could experience significant cooling even as the global average temperature rises. Not an ice age, but a disruption severe enough to alter agricultural patterns, energy demand, and extreme weather frequency. All of these cascading effects start in the same place: the Southern Ocean. The engine at the bottom of the world, the system that we ignored, failed to name, and are only now beginning to understand. The 2025 Nature paper made one more point that deserves emphasis. These changes are not happening in isolation. They're connected. The ice shelf loss feeds the freshwater cap that slows the overturning circulation. The circulation slowdown reduces heat transport to the deep ocean, which warms the surface, which melts more ice. The sea ice decline disrupts ecosystems that depend on it, while simultaneously altering the albedo, the reflectivity of the polar region, causing it to absorb more solar energy. Each change amplifies the others. The system is not experiencing a single problem, it is experiencing a cascade, and cascades by their nature accelerate. Which brings us to the final question, the one that matters more than any fact or figure or scientific paper. What do we not know? What are we still missing? And is there still time to do anything about it? The honest answer is that we don't know nearly enough, and what we don't know might matter more than what we do. The Southern Ocean is the least studied major body of water on the planet. It covers 20 million square kilometres and reaches depths of over 7,000 metres. It is surrounded by the most inhospitable conditions on Earth, scoured by storms that would sink most vessels, locked behind ice that blocks access for months of the year, and located so far from any research base that simply getting there is a logistical feat. We have better maps of the surface of Mars than we do of the Southern Ocean floor. We have more detailed temperature records for the upper atmosphere than we do for the deep waters around Antarctica. The organisms that live in the abyss remain overwhelmingly undescribed, unnamed, unstudied. Of the biological samples collected during the 2025 Necton expedition, 70% have not yet been assessed. And that expedition covered a vanishingly small fraction of the total seafloor. The models that predict how the Southern Ocean will behave in the coming decades are the best tools we have, but they are limited. The 2023 Nature paper that flagged the abyssal slowdown used state-of-the-art climate simulations, and those simulations have already been outpaced by observations. The actual rate of change in Antarctic bottom water production has exceeded what the models projected. The 2025 PNAS paper showing circulation reversal documented a phenomenon that most models did not predict would occur this soon. This is a pattern that repeats throughout Antarctic science. The observations keep outrunning the models, not by a little, by a lot. The ice is melting faster than predicted. The circulation is slowing faster than predicted. The ecosystems are responding faster than predicted. And the feedback loops that connect these changes are stronger and more tightly coupled than anyone anticipated. In January of 2025, a drilling project in Antarctica reached a milestone that scientists had been working toward for years. An international team extracted an ice core from the Antarctic interior that contains a continuous record of Earth's climate, stretching back over 1 million years. Previous ice cores had gone back about 800,000 years, but this new core pushes deeper into the past, into a time when the rhythm of Earth's ice ages was fundamentally different from what came later. Trapped inside this ice are tiny bubbles of ancient atmosphere. Each bubble is a time capsule, preserving the exact composition of the air at the moment the snow fell and compacted into ice. By analysing these bubbles, scientists can reconstruct the concentration of carbon dioxide and methane in the atmosphere going back 1 million years. They can see how the climate system responded to natural fluctuations in greenhouse gases. They can compare what happened in the distant past to what is happening now, and those comparisons, early as they are alarming. The concentration of CO2 in the atmosphere today, roughly 425 parts per million, is higher than anything recorded in the ice core record, higher than any point in the last 1 million years. The rate of increase is also unprecedented. The natural carbon cycle produces slow, gradual changes over tens of thousands of years. What humans have done in the last 2 centuries looks, in the ice core record, like a vertical spike, a sudden jump that has no analogue in the geological past. The 1 million-year record matters because it gives context. It shows how the Southern Ocean responded to past changes in CO2 and temperature, and the emerging evidence suggests that the Southern Ocean's behaviour during past warm periods was more dynamic, more volatile, and more consequential than previously understood. The Antarctic circumpolar current sped up during warm periods and slowed during cold ones. The ice sheets responded not gradually, but in abrupt pulses. The deep circulation fluctuated in ways that amplified the warming rather than dampening it. This is the context within which our current changes are occurring. We are not just warming the planet, we are warming it faster and harder than anything in the geological record. And the Southern Ocean, the system that has always responded to warming by absorbing it and redistributing it, is responding in ways that suggest it may be reaching the limits of its capacity to do so. And then there are the methane seeps. In recent years, researchers have discovered plumes of methane gas bubbling up from the seafloor in the Southern Ocean. Methane is a greenhouse gas roughly 80 times more potent than CO2 over a 20-year period. The discovery of methane seeps around Antarctica raises a deeply unsettling possibility. Could the warming of the deep ocean trigger the release of methane from frozen deposits on the seafloor? Around the world's continental margins, enormous quantities of methane are locked in ice-like structures called methane hydrates, or clathrates. These deposits are stable at low temperatures and high pressures, but when the water around them warms they can destabilize. The methane escapes from the ice lattice and bubbles up through the water column. If enough of it reaches the atmosphere, it could trigger additional warming, which could destabilize more hydrates, creating another feedback loop. The methane seeps discovered in the Southern Ocean are still being studied. Scientists do not yet know whether they represent a new phenomenon triggered by recent warming or a natural process that has been occurring for a long time without being detected. But the fact that they exist at all, in waters that are warming faster than the models predicted, is reason enough for concern. There are also the unknowns that we don't even know how to frame yet. The Southern Ocean interacts with the atmosphere, the cryosphere, the biosphere, and the solid Earth in ways that are still being mapped. The subglacial lakes, the microbial communities living in the total darkness under kilometers of ice, the volcanic activity beneath the ice sheet that may be contributing to basal melting in ways we cannot measure from the surface, the interactions between the ozone hole, which is recovering, and the atmospheric circulation patterns that drive the westerly winds, which in turn drive the Antarctic circumpolar current. Each of these factors introduces uncertainty into our projections. What we do know is that the window for action is narrowing. The High Seas Treaty, formerly known as the Agreement on the Conservation and Sustainable Use of Marine Biological Diversity of Areas Beyond National Jurisdiction, was adopted by the United Nations in 2023 after nearly 2 decades of negotiation. As of September 2025, enough countries had ratified the treaty for it to become legally binding in January 2026. This treaty creates a framework for establishing marine protected areas on the high seas, including the Southern Ocean. It is the first international legal instrument that could meaningfully protect large swaths of the deep sea from exploitation. But a framework is not protection. The marine protected area proposals for the Southern Ocean have been stalled at the Commission for the Conservation of Antarctic Marine Living Resources for years, blocked by member nations with fishing interests. Only 13% of the Southern Ocean is currently protected. The pending proposals, if adopted, would raise that to about 26%. That is progress, but it leaves 3/4 of the ocean unprotected, and protection from fishing, as important as it is, does nothing to address the fundamental threat. The Southern Ocean's biggest problem is not fishing boats, it is the warming atmosphere. It is the CO2 we have already emitted. It is the heat already stored in the deep ocean. It is the fresh water already pouring off the melting ice sheet. These are forces that no marine protected area can contain. The Southern Ocean was the last ocean we agreed to name. It was the last major body of water to appear on our maps. It is still the least explored, the least understood, and the least protected of all the oceans, and it is, by almost any measure, the most important. It absorbs our heat, it buries our carbon, it feeds oxygen into the deep sea, it drives the currents that regulate the climate of every continent. It supports ecosystems that we have only just begun to discover, and it is changing right now in real time, in ways that will affect every human being on the planet for generations to come. We were wrong about this ocean. We were wrong about what it was, what it did, and how fast it could change. We were wrong about the water, about the ice, about the creatures that live in the dark. We were wrong about how much it could absorb before it started to push back. And maybe the most troubling thing we were wrong about was this. We assumed it would wait for us. We assumed we had time to study it, to name it, to understand it, to protect it. We assumed the engine at the bottom of the world would keep running no matter what we did to the rest of the planet. The Southern Ocean does not care about our assumptions. It does not care about our maps or our treaties or our climate models. It is a physical system, governed by the laws of thermodynamics and fluid dynamics and chemistry. It responds to the conditions we create, and the conditions we have created are pushing it toward a state that has no precedent in human history. But the story is not over. The ice core drilling continues. The research vessels are deploying sensors into the deep. The satellites are watching. The models are improving. The treaties are advancing. The species are being named. The mechanisms are being understood. The picture is getting clearer, even as the situation gets more urgent. In 1937, the International Hydrographic Organization recognized the Southern Ocean. In 1953, they took it back. In 2021, the world finally put it on the map for good. It took 68 years to acknowledge what was always there. The question now is whether we will take another 68 years to act on what we know. Because the Southern Ocean has been patient with us, but the science is clear. That patience is running out. The circumpolar current still flows. The cold water still sinks, even if less of it than before. The phytoplankton still bloom every spring, turning the surface green, pulling carbon from the air. The emperor penguins still march across the ice to raise their chicks, even if the ice is less reliable than it used to be. The ice fish still swim through the dark, with antifreeze in their blood. The colossal squid still hunts in the deep. And somewhere, on the seafloor beneath the spot where an iceberg the size of a country broke free, a carnivorous sponge with tiny hooks is waiting in the dark for its next meal. The Southern Ocean is still here. It is still working. It is still the engine, but the engine is running differently now. And what happens next depends, more than most people realize, on what we do in the next 10 years. The ocean that didn't exist on our maps for most of modern history turns out to be the one that holds our future. We just took a very long time to notice. Sleep well. If you are still listening, there is more to tell. Because every chapter of this story has layers we only touched on the surface, and the deeper you go, the stranger and more extraordinary this ocean becomes. Let's go back to the very beginning, to the moment the Southern Ocean was born. 34 million years ago, at a time geologists call the Eocene-Oligocene boundary, Antarctica was a different world. It was green, not the white wasteland of ice and rock we picture today, but a living continent covered in temperate forests, southern beech trees, conifers, ferns. The coast was mild enough to support diverse plant and animal life. There were marsupials on Antarctica. There were forests that looked like what you would find today in Tasmania or Patagonia. At that time, Antarctica was still connected to South America by a land bridge, and that connection meant that the warm ocean currents from the tropics could flow all the way down to the southern coast of the continent, keeping Antarctica warm, keeping the forest alive, preventing the ice from forming. But the continents were drifting. South America was pulling away. The gap between the Antarctic Peninsula and the southern tip of South America, what we now call the Drake Passage, was slowly widening, inch by inch, year by year, over millions of years, and then somewhere around 34 million years ago, the gap became wide enough for water to flow through it unimpeded. The Antarctic circumpolar current formed, and everything changed. The warm tropical water that had been reaching Antarctica was blocked. The cold water that had been mixing with the warm was suddenly free to circulate around the entire continent without interruption. The current built on itself, reinforced by the fierce westerly winds, until it became the largest current on Earth. Antarctica was sealed off, cut off from the warmth of the rest of the planet by a wall of cold, fast-moving water that has not stopped flowing in 34 million years. The forests died, the marsupials disappeared, the ice grew, first on the mountain tops, then spreading down to the coast, then pushing out onto the continental shelf and beyond. The Antarctic ice sheet formed, locked in by the circumpolar current, growing thicker and heavier century after century until it became the largest single mass of ice on the planet. About 26.5 million cubic kilometres of frozen water. Enough to raise global sea levels by roughly 58 metres if it all melted. And for 34 million years the engine ran. The current flowed. The ice grew and retreated with the natural rhythms of Earth's orbital cycles, the Milankovitch cycles that drive the ice ages. But the fundamental system persisted. Cold water sank. Deep water formed. The carbon got buried. The heat got redistributed. The ice stayed. Until now. What makes the current crisis different from anything in the last 34 million years is not just the warming itself, but the speed of the warming. Earth has been warmer than it is now. There have been periods in the distant past when CO2 levels were higher, temperatures were higher, and Antarctica had less ice. But those changes played out over hundreds of thousands of years. The organisms in the Southern Ocean had time to adapt. The circulation had time to adjust. The ice had time to retreat and reform. What we are doing is compressing millions of years of natural change into centuries, and in some cases, decades. The species that evolved in the deep Southern Ocean over millions of years are now facing temperature changes and oxygen declines that are playing out over the span of a single human generation. There is no time to adapt. There is no precedent in their evolutionary history for what is happening to them. The ice fish, those remarkable creatures with antifreeze glycoproteins in their blood that prevent ice crystals from forming in their tissues, evolved this adaptation over millions of years in water that has been near or below freezing for as long as their lineage has existed. They have lost the ability to make hemoglobin. Their blood is translucent. They are the only known vertebrates that lack red blood cells. They survive because the cold water holds enough dissolved oxygen that they can absorb it directly through their skin and gills without needing hemoglobin to carry it. But this means they are exquisitely sensitive to changes in water temperature and oxygen levels. Even a slight warming reduces the oxygen carrying capacity of the water. A slight decline in dissolved oxygen from reduced bottom water formation could push them past a threshold they cannot cross. They are specialists, masters of their niche, and their niche is disappearing. The same is true for the communities living beneath the ice shelves. The organisms discovered under the George VI ice shelf in 2025, those anemones and bryozoans and sea spiders, were living in conditions that had been stable for thousands of years. Constant cold, constant darkness, constant pressure. They built their communities based on the assumption that those conditions would persist. And now, as ice shelves collapse and warm water intrudes, those assumptions are being violated. It is possible, maybe even likely, that some of these species will go extinct before they are even formally described. The taxonomists are working as fast as they can, but the pace of environmental change may outstrip the pace of discovery. We might lose species that we never knew existed. And then there is the question of what else is down there that we haven't found yet. The Ocean Census Initiative aims to discover 100,000 new marine species over the next decade. The Southern Ocean is expected to contribute a disproportionate share of those discoveries, simply because so little of its deep water has been explored, but the 100,000 is just a number. The real total of undiscovered species in the ocean as a whole is estimated to be in the millions, and the Southern Ocean, with its extreme conditions and long evolutionary isolation, is likely home to an unusually high proportion of endemic species, organisms that live there and nowhere else. Every expedition to the deep Southern Ocean has found something new, Every camera drop has revealed organisms that were not in the textbooks: the carnivorous sponge, the zombie worms, the Elvis worms, the organisms that thrive in total darkness, feeding on chemical energy and the slow rain of organic matter from above, the microbes that live inside the ice itself, in tiny veins of liquid water within the crystal lattice, surviving in conditions that would kill almost anything else. These are not just curiosities, they are potential sources of biomedical compounds, genetic resources and insights into the fundamental limits of life. The antifreeze proteins in icefish blood have applications in organ preservation and cryogenics. The enzymes produced by cold-adapted bacteria have uses in industrial biotechnology. The study of how organisms survive in extreme cold and darkness informs our understanding of where life might exist elsewhere in the solar system, in the subsurface oceans of Europa and Enceladus, moons of Jupiter and Saturn that may harbour conditions similar to the deep Southern Ocean. When we talk about protecting the Southern Ocean, we are not just talking about penguins and whales, as important as those animals are. We are talking about a biological library that has been accumulating volumes for millions of years, and that we have only just started to read. Losing even a fraction of that library before we understand what it contains would be a tragedy of the highest order. Now let's return to the water itself, because there is one more dimension to the Southern Ocean story that ties everything together, and it involves something that happens every single year, like clockwork, in the waters around Antarctica. Spring. When the southern hemisphere's spring arrives, usually around September and October, the sea ice begins to retreat. Sunlight floods the surface waters for the first time in months, and the phytoplankton bloom. This is not a subtle event. The Southern Ocean's spring bloom is one of the largest biological events on the planet. Trillions upon trillions of microscopic photosynthetic organisms erupt across millions of square kilometres of ocean surface, turning the water green and consuming staggering quantities of carbon dioxide. These blooms are visible from space. Satellite images show the Southern Ocean transforming from dark blue to vivid green as the phytoplankton multiply. The blooms are fueled by nutrients: iron, nitrogen, silica, phosphorus. These nutrients come from the deep water that upwells to the surface, water that has been accumulating dissolved minerals during its centuries-long journey through the abyss. The Southern Ocean is one of the few places on Earth where deep ocean nutrients reliably reach the sunlit surface, creating conditions for explosive biological productivity. The iron is especially important. Iron is a limiting nutrient in much of the Southern Ocean, meaning that phytoplankton growth is capped by the amount of iron available, rather than by light or other nutrients. The iron comes from multiple sources: upwelling deep water, melting sea ice, which concentrates trace metals, dust blown from continental deserts, although this source is minimal in the southern hemisphere, and increasingly meltwater from the Antarctic ice sheet itself, which carries iron-rich sediment from the continental bedrock. As the ice sheet melts faster, more iron enters the ocean. This could, paradoxically, stimulate more phytoplankton growth, more blooms, more carbon fixation, a natural feedback loop where melting ice produces more biological carbon removal. But the picture is more complex than that. Increased meltwater also freshens the surface ocean, creating a more stable surface layer that is harder for nutrients to penetrate from below. The fresh water sits on top like a lid, trapping the nutrients in the deep water where the phytoplankton cannot reach them. So while iron increases, other nutrients might decrease. The net effect on phytoplankton productivity is uncertain, and the species composition of the blooms matters enormously. Different phytoplankton species have different carbon export efficiencies. Diatoms, the large silica-shelled phytoplankton that dominate many Southern Ocean blooms, are heavy. They sink quickly when they die, carrying carbon efficiently to the deep ocean. But smaller species, like flagellates, are lighter and more likely to be recycled in the upper ocean, releasing their carbon back to the atmosphere before it reaches the deep. Climate change is shifting the balance of phytoplankton communities. Warming water favours smaller species. Reduced sea ice changes the timing and location of blooms. Changes in upwelling alter the nutrient supply. The net result is that the biological pump, the mechanism by which the Southern Ocean removes carbon from the atmosphere and sequesters it in the deep, may become less efficient even as the total amount of phytoplankton grows. More green water, less carbon buried. A system that looks productive on the surface but is leaking from the bottom. This is the kind of nuance that gets lost in simple narratives about climate change. The Southern Ocean is not a machine with an on-off switch. It is a complex adaptive system with hundreds of interacting variables, and the way it responds to warming is not linear, not predictable, and not reassuring. And hovering over all of these biological and physical changes is one more factor that deserves attention. The ozone hole. The Antarctic ozone hole, first discovered in the 1980s, was caused by chlorofluorocarbons and other ozone-depleting chemicals that accumulated in the stratosphere and destroyed the protective ozone layer over Antarctica. The Montreal Protocol, signed in 1987, banned these chemicals, and the ozone layer has been slowly recovering ever since. The hole is still there, but it is shrinking. Scientists expect it to fully heal by roughly the middle of the century. But the ozone hole did something unexpected while it was open. By cooling the stratosphere over Antarctica, it shifted the jet streams and strengthened the westerly winds that blow over the Southern Ocean. These stronger winds push the Antarctic circumpolar current faster and enhance the upwelling of deep water. They also pushed more warm water toward the Antarctic coast, contributing to ice shelf melting. As the ozone hole heals, the westerly winds may weaken or shift back toward their pre-ozone hole patterns. This would change the dynamics of the ACC, the overturning circulation, the upwelling of nutrients, and the transport of warm water toward the continent. It could help slow some of the changes we have been discussing, or it could interact with climate change in ways that nobody has modelled yet, because the healing of the ozone hole and the intensification of greenhouse warming are happening simultaneously, and their effects are sometimes complementary and sometimes opposing. The Southern Ocean is being pushed and pulled by forces acting on different timescales and in different directions. CO2 warming, ozone recovery, ice sheet melting, circulation changes, ecosystem shifts, geological processes, atmospheric dynamics. All of these forces interact, and the interactions produce surprises. This is why the million-year ice core matters so much. It provides context. It shows us how the system responded to past changes and gives us a baseline against which to measure what is happening now. But even the ice core has its limits. It can tell us what the atmosphere looked like a million years ago. It cannot tell us what the deep ocean was doing at the same time, because the ocean leaves different kinds of records in different kinds of archives. Sediment cores from the seafloor, chemical signatures in coral skeletons, fossilized shells of foraminifera, tiny organisms whose chemistry records the temperature and composition of the water they lived in. Piecing together the full picture of the Southern Ocean's past requires integrating all of these archives, and the work is ongoing. Every year brings new cores, new analyses, new data points that refine our understanding of how this system has behaved over geological time. And every year, the urgency of that understanding grows, because the system is changing faster than we can study it. There is a cruel irony in all of this. The Southern Ocean is the most important ocean on Earth for regulating the climate, and it is the one we know the least about. It is the one we named last, studied last, mapped last, and protected last. And it is the one that is changing the fastest, in ways that will affect every person on the planet, whether they have ever heard of it or not. But knowledge is accumulating. Research vessels are braving the storms. Autonomous floats are drifting through the deep, measuring temperature and salinity and oxygen in places where no instrument has ever been. Satellites are tracking the ice with centimetre precision. International collaborations are forming, sharing data, comparing models, pushing the frontier of understanding. The Southern Ocean Observing System, an international network of scientists and institutions, is building a comprehensive monitoring framework for the entire circumpolar region. The Argo Float program has deployed thousands of autonomous instruments across the global ocean, including hundreds in the Southern Ocean, measuring conditions from the surface to 2,000 meters depth. Newer deep Argo floats are going even deeper, down to 6,000 meters, into the abyss where Antarctic bottom. Water is born and begins its long journey across the planet. The picture is getting clearer. Not fast enough. Not detailed enough. Not in time to prevent all of the changes that are already in motion, but clearer. And perhaps that is the most important thing to understand about the Southern Ocean. It is not a mystery that will be solved all at once. It is a book that is being written in real time, by the ocean itself, in a language that we are still learning to read. The 1937 recognition was a first word. The 1953 reversal was an erasure. The 2021 declaration was a new beginning. And everything that has happened since, the discoveries, the alarms, the surprises, the tipping points, the hidden worlds beneath the ice, is the chapter we are living through right now. We were wrong about this ocean, about so many things. But being wrong is how science works. You observe, you hypothesize, you test, you get surprised, you revise, and you keep going. The Southern Ocean has been surprising us since the first sailor ventured south of 60 degrees and felt the water change beneath the hull. It will keep surprising us. The question is whether we will keep listening. The current still flows. The water still sinks. The ice still forms and breaks and forms again. The phytoplankton still bloom in the Antarctic spring, painting the ocean green. The penguins still waddle across the ice. The colossal squid still drifts through the deep. And somewhere on the abyssal plain, in water just above freezing in total darkness, at a pressure that would crush a submarine, a sponge with tiny hooks is waiting. The Southern Ocean is the engine of the world, the engine that we forgot, the engine that we are only now, finally, beginning to understand. And it is telling us something, in the temperature of its water, in the speed of its currents, in the chemistry of its ice, in the silence of its empty nesting colonies. In the methane bubbling from its seafloor, it is telling us that the world we thought we understood is changing in ways that we did not anticipate. And the ocean that we left off our maps for 68 years is the one that holds the key to what happens next. Listen to the water. It knows what's coming. Sleep well. There is a detail about the Antarctic circumpolar current that deserves more attention, because it reveals just how interconnected the Southern Ocean is with the rest of the planet's climate system. The ACC does not flow in a simple, uniform ring around Antarctica. It meanders. It forms eddies. It develops jets, narrow ribbons of faster-moving water embedded within the broader current, like express lanes on a highway. These jets and eddies are not just wrinkles in the flow. They are the primary mechanism by which heat and salt are transported across the current, from the warm subtropical waters to the north to the cold polar waters to the south. Think of the ACC as a barrier with holes in it. The jets and eddies are the holes. Warm water leaks through them, carrying heat toward Antarctica. Cold water leaks out through them, carrying nutrients and dissolved carbon toward the lower latitudes. The size, number, and intensity of these eddies determine how much heat gets through the barrier. And as the winds that drive the ACC have strengthened over the past few decades, partly due to climate change and partly due to the ozone hole, the eddies have changed. Stronger winds do not just make the current faster, they make it more turbulent. More eddies form, the eddies grow larger and more energetic, and more warm water sneaks through the barrier toward Antarctica. This is called eddy compensation, and it is one of the reasons why the Southern Ocean's response to climate change has been so much more complex than simple models predicted. Early climate models treated the ACC as a relatively uniform current that would respond predictably to changes in wind forcing. but the real ACC is a chaotic, turbulent system where eddies play a dominant role, and the eddy activity introduces non-linear dynamics that are fiendishly difficult to model. A team of researchers using satellite altimetry data, which measures the height of the ocean surface with millimetre precision, has tracked the evolution of eddies in the ACC over the past 3 decades. They found that the eddy kinetic energy, a measure of how active and intense the eddies are, has increased significantly. More energy in the eddies means more heat crossing the barrier, more heat reaching the Antarctic continental shelf, more warm water getting underneath the ice shelves and melting them from below. This is the pipeline that connects the global atmosphere to the Antarctic ice sheet. Greenhouse gases warm the atmosphere. The atmosphere warms the Southern Ocean surface and strengthens the winds. The stronger winds generate more energetic eddies in the ACC. The eddies transport more warm water across the current barrier toward Antarctica. The warm water reaches the continental shelf and flows under the ice shelves. The ice shelves thin, crack, and collapse. The glaciers behind them accelerate. Sea level rises. Each link in this chain has been individually documented by research teams around the world. The challenge is understanding how they all interact, how fast the chain operates, and whether there are thresholds along the way where a gradual increase in one variable triggers an abrupt change in another. There is another dimension to the circulation story that often gets overlooked. The Southern Ocean does not just move water horizontally around Antarctica, it moves water vertically. The overturning circulation, the sinking of dense water, and the rising of deep water creates a vertical conveyor that connects the surface to the abyss. And this vertical circulation has its own dynamics, its own vulnerabilities, and its own surprises. When scientists talk about the overturning slowing down, they are talking about the weakening of this vertical exchange. Less water sinking means less water rising, and less water rising means fewer nutrients reaching the surface, less carbon being absorbed, less oxygen being delivered to the deep. The vertical conveyor is the heartbeat of the Southern Ocean, and it is beating more slowly. But the slowdown is not uniform. Different parts of the Southern Ocean are experiencing different rates of change. The Weddell Sea, where the densest Antarctic bottom water forms, has seen the most dramatic reductions. The Ross Sea, another major formation region, has been somewhat more stable but is showing signs of change as well. The smaller formation sites around the Antarctic coast are responding in varied ways depending on local conditions, ice shelf geometry, and wind patterns. This patchiness makes the system harder to monitor and harder to predict. You cannot measure the overturning circulation at one location and assume you know what it is doing everywhere else. You need a comprehensive observing network that covers the entire circumpolar region, and that network is still being built. The Southern Ocean Observing System has made remarkable progress, but it is working against the clock. Every year of incomplete data is a year of change that goes unrecorded, and the changes, as we have seen, are accelerating. Consider the krill. We mentioned earlier that Antarctic krill are declining in parts of the Southern Ocean, but the full story is more nuanced and more alarming than a simple population decline. Antarctic krill, Euphausia superba, is not just another marine organism. It is the keystone species of the Southern Ocean ecosystem. The total biomass of Antarctic krill is estimated at around 300 to 500 million tons. That makes them one of the most abundant animal species on the planet, by weight. They are the primary food source for virtually every large predator in the Antarctic. Blue whales, the largest animals that have ever lived, can eat up to 4 tons of krill per day. Humpback whales, minke whales, leopard seals, crab-eater seals, Adelie penguins, emperor penguins, petrels, albatrosses, squid, and dozens of species of fish all depend on krill, either directly or indirectly. Krill also play a critical role in the carbon cycle. They feed on phytoplankton at the surface and produce fecal pellets that sink rapidly to the deep ocean, transporting carbon from the surface to the abyss far more efficiently than dead phytoplankton alone. Krill also undergo a daily vertical migration, swimming from the deep ocean to the surface each night and back down each morning, a journey that spans hundreds of meters, and that further helps to mix the water column and transport nutrients and carbon. The krill fishery in the Southern Ocean has been expanding. Demand for krill oil, used in dietary supplements, and krill meal, used in aquaculture feed, has driven increased fishing pressure. The fishery is managed by CCA-MLR, but there are concerns that the catch limits do not adequately account for the combined effects of fishing and climate change on krill populations. Research published in recent years has shown that krill recruitment, the number of young krill that survive to adulthood, is strongly correlated with sea ice extent. More ice means more algae growing on the underside of the ice, which means more food for larval krill. Less ice means less food, lower survival rates, and fewer adults entering the breeding population the following year. With sea ice declining to record lows since 2016, krill recruitment has been under sustained pressure, and because krill are so central to the food web, their decline cascades through the entire ecosystem. Fewer krill means less food for penguins, less food for whales, less food for seals, less efficient carbon transport to the deep ocean. The ripple effects reach into every corner of the Antarctic marine ecosystem. There is also the question of what replaces krill. As conditions change, other organisms may fill some of the ecological niches currently occupied by krill. Salps, gelatinous filter feeders that thrive in warmer ice-free water, have been increasing in some parts of the Southern Ocean, but salps are not an equivalent substitute for krill. They are less nutritious, they are less efficient at transporting carbon, and many of the predators that depend on krill cannot eat salps. A Southern Ocean dominated by salps instead of krill would be a fundamentally different ecosystem, less productive, less diverse, and less effective at cycling carbon. This ecological shift is not a distant possibility. It is happening now in some regions. The Antarctic Peninsula, the finger of land that reaches northward towards South America, has warmed faster than almost any other place on the planet over the past 50 years. Krill populations in the waters around the peninsula have declined. Salp populations have increased. Penguin colonies that were once thriving are shrinking. The ecosystem is transitioning in real time from one state to another, and this transition is irreversible on any human timescale. Even if we stopped all emissions tomorrow, the warming that has already occurred will persist in the Southern Ocean for centuries. The deep water that is currently forming will carry the signature of today's conditions into the abyss, where it will circulate for 500 to 1,000 years before returning to the surface. The decisions we make in the next decade will echo through the Southern Ocean for a millennium. This is perhaps the most important thing to understand about the Southern Ocean. It operates on timescales that are utterly foreign to human politics, human economics, and human attention spans. The heat we emitted in the 1980s is still sinking into the deep ocean right now. The carbon we emitted in the 1990s is still being transported through the abyss. The ice that is melting today will affect the overturning circulation for centuries to come. We live in the present. The Southern Ocean lives in deep time. And the gap between our timescale and its timescale is the gap that makes this crisis so difficult to address. By the time the consequences of our actions become fully visible, the opportunity to prevent them will have passed decades ago. That is why the research matters. That is why the monitoring matters. That is why the treaties matter. Not because they will solve the problem immediately, but because they give us the information and the tools to make decisions that will echo through the centuries in the right way instead of the wrong way. The Southern Ocean has been absorbing our mistakes for generations. It has been patient and generous and silent. But it is not infinite, and the signals it is sending through the temperature of its water, the speed of its currents, the chemistry of its ice, the health of its ecosystems are growing louder. We were wrong about this ocean, but we are learning, and what we do with what we learn will determine whether the engine at the bottom of the world keeps running or whether it becomes something else entirely. something we are not prepared for. The water is still cold, the current still flows, the ice still forms, and the krill still swarm, and the penguins still call across the frozen sea in the Antarctic night. But the clock is ticking, and the Southern Ocean is the clock. Sleep well. There is one more story from the Southern Ocean that has never been told properly. It involves the whales. Before the age of industrial whaling, the Southern Ocean was home to the largest concentration of great whales anywhere on the planet. Blue whales, fin whales, humpback whales, right whales, sei whales, sperm whales, minke whales. They came in numbers that are difficult to comprehend today. Estimates suggest that before whaling began, the Southern Ocean supported populations of several million great whales. The biomass was enormous. The ecosystem was built on their presence, and then over the course of about a century, humans killed most of them. Industrial whaling in the Southern Ocean peaked in the early to mid-20th century. Factory ships would anchor in Antarctic waters and process whales around the clock. Entire populations were decimated. The blue whale population was reduced to less than 1% of its original size. The southern right whale was hunted to the brink of extinction. The fin whale, the Essie whale, and the humpback were all driven to fractions of their historical numbers. The whaling era officially ended in the Southern Ocean with the establishment of the Southern Ocean Whale Sanctuary in 1994, and commercial whaling moratoriums had been in place since 1986. Since then, some whale populations have been recovering. Humpback whales in particular have made a remarkable comeback, with some populations approaching pre-whaling levels. But here is what nobody expected. The recovery of the whales is changing the ocean itself. Whales are not just passengers in the marine ecosystem, they are ecosystem engineers. They play an active role in cycling nutrients through the ocean in ways that have profound effects on productivity and carbon sequestration. When a whale dives to depth to feed and then returns to the surface to breathe, it carries nutrients with it. The iron and nitrogen in its fecal plumes released near the surface fertilize the phytoplankton. This is called the whale pump. And in the Southern Ocean, where iron is the limiting nutrient for phytoplankton growth, the whale pump can significantly enhance primary productivity. Before whaling, the whale pump was a major source of iron recycling in the Southern Ocean. Millions of whales feeding on krill and releasing nutrient-rich waste at the surface created a positive feedback loop. More whales meant more nutrient recycling, which meant more phytoplankton, which meant more krill, which meant more whales. The system was self-reinforcing. When the whales were removed, that pump stopped. Less iron was recycled. Phytoplankton productivity may have declined, at least in some areas. The krill population, paradoxically, may have also declined, because the nutrient cycling that supported the entire food web was disrupted at its foundation. Now, as whale populations recover, the pump is restarting, and researchers are beginning to document what they call the whale carbon pump, the idea that recovering whale populations could meaningfully increase the Southern Ocean's capacity to absorb and sequester carbon dioxide. Here is how it works. Whales eat krill. They release iron-rich feces at the surface. The iron fertilizes phytoplankton. The phytoplankton bloom, absorbing CO2. Some of the phytoplankton die and sink, carrying carbon to the deep ocean. The krill that eat the phytoplankton also produce sinking fecal pellets, and when the whales themselves die, their massive bodies sink to the seafloor, each one carrying tons of carbon that will be locked in the sediment for centuries or millennia. A single great whale sequesters an average of about 33 tons of carbon over the course of its lifetime. Not in its diet, in its body. When it dies and sinks, that carbon goes to the bottom. By comparison, a tree absorbs about 22 kilograms of carbon per year. A single whale is worth thousands of trees in terms of carbon sequestration. An International Monetary Fund study estimated the value of the carbon sequestration services provided by great whales at roughly $2 million per individual whale over its lifetime. Multiply that by the millions of whales that were killed during the whaling era, and you begin to get a sense of the ecological and economic cost of what was lost. The recovery of southern ocean whale populations is therefore not just a conservation success story, it is a climate strategy. Every whale that returns to the Southern Ocean is a carbon sequestration machine, a nutrient pump, and an ecosystem engineer that helps the ocean do its job of absorbing CO2 and maintaining productivity. But whale recovery takes time. Great whales are slow breeders. They have long gestation periods, produce one calf at a time, and take years to reach sexual maturity. Even with full protection, it will take decades to centuries for populations to return to pre-whaling levels. And during that time, the ecosystem they are recovering into is changing around them. The krill they depend on are declining. The sea ice they navigate is shrinking. The water is warming. The whales are coming back. But they are coming back to a different ocean than the one their ancestors left. And this gets to the heart of the challenge facing the Southern Ocean. Everything is connected. The whales need the krill need the ice needs the cold needs the circulation needs the density contrast between surface water and deep water, the density contrast needs the salt needs the freezing process, and the freezing process needs temperatures that are, in some parts of the Southern Ocean, no longer cold enough. Pull one thread and the whole system shudders. We have been pulling threads for over a century, pulling out the whales, pulling out the krill, pumping in the carbon, pumping in the heat, melting the ice, freshening the water, slowing the circulation, warming the abyss. And now the Southern Ocean is responding, not with a single dramatic event that makes the evening news and is forgotten by next week, but with a slow, inexorable shift in the fundamental processes that make this ocean what it is. The kind of shift that operates on timescales longer than a political career, longer than a human lifetime, longer than the memory of any institution or government. This is why the story of the Southern Ocean is ultimately a story about time, about the vast difference between the timescale on which humans operate and the timescale on which the ocean operates, about the decisions we make in years and the consequences that play out over centuries, about the gap between what we can see and what is happening in the dark under thousands of meters of water, where the densest water on Earth is slowly, quietly failing to form the way it used to. The Southern Ocean has been the planet's thermostat, its carbon vault, its oxygen factory, its nutrient highway, and its climate memory for 34 million years. It has absorbed asteroid impacts and survived ice ages. It has weathered changes in atmospheric CO2 that spanned millions of years. It has been resilient in ways that almost no other system on Earth can match. But resilience has limits, and we are testing those limits now at a rate that has no precedent in the geological record, not in the ice cores, not in the sediment cores, not in the fossil record, not in 34 million years of continuous operation. The engine is still running, but the warning lights are on. The temperature gauges are climbing, the pressure is building, and the operators, that is us, are only just now looking at the dashboard for the first time. We were wrong about the Antarctic Ocean. We were wrong about how many oceans there are. We were wrong about what lives in the deep. We were wrong about how the ice behaves. We were wrong about how much heat the water can hold. We were wrong about how fast the circulation can change. We were wrong about what happens when you push a system this large past its breaking point. But the Southern Ocean is still there, still circling Antarctica, still connecting the world's oceans, still absorbing heat and carbon and oxygen and pumping it into the deep, still supporting life in places we have only just begun to explore. It is still the engine, and it is still, despite everything, working. For now, sleep well. But perhaps the strangest chapter in the Southern Ocean story is the one being written right now, beneath the ice, in places so remote and so hostile that only robots can go. In 2024 and 2025, teams of scientists deployed autonomous underwater vehicles torpedo-shaped robots equipped with sonar, cameras, and sensors beneath the floating ice shelves of West Antarctica. These vehicles navigated through cavities between the ice shelf and the seafloor, mapping terrain that no human eye had ever seen, measuring water temperatures and currents in spaces too dangerous and too remote for any crewed vessel to enter. What they found changed the understanding of how ice shelves melt. The prevailing model had been relatively straightforward. Warm water flows under the ice shelf. The warm water contacts the bottom of the ice melts. The meltwater, being lighter than seawater, rises along the underside of the ice and flows out to the open ocean. The reality turned out to be far more complicated. The cavity beneath an ice shelf is not a simple open space. It is an intricate landscape of ridges, channels, crevasses, and terraces. Warm water does not flow in evenly. It follows channels, concentrates in some areas and bypasses others. The melting is patchy, intense in some spots and minimal just meters away. The autonomous vehicles discovered that the grounding zones, the places where the ice shelf meets the bedrock and transitions from floating ice to grounded ice, are experiencing the most intense melting. These grounding zones are the anchors that hold the entire system in place, and they are being undermined from below by warm water that seeps into channels and crevices that are too small to detect from the surface. This is why satellite measurements of ice shelf thickness, which average over large areas, have consistently underestimated the rate of change at the grounding line. The action is happening at a scale smaller than satellites can resolve, in narrow channels and thin crevices where warm water concentrates and eats away at the ice like acid-dissolving rock. The Thwaites Glacier's ice shelf, the one we discussed earlier as the so-called Doomsday Glacier, was one of the primary targets of these autonomous surveys. The results confirmed that the grounding zone is retreating faster than surface observations suggested. The ice is thinner where it meets the bedrock. The warm water pathways are more extensive than models predicted. The system is more vulnerable than the satellite data alone would indicate. And beneath the ice, in the dark water between the seafloor and the ice ceiling, the robots found something else. Life. Not the vibrant communities discovered under the George VI ice shelf, but a sparser, more enigmatic community of organisms living in one of the most extreme environments on the planet, microbial mats on the rocks, small invertebrates clinging to surfaces, fish dark and slow-moving, navigating a world of perpetual cold and darkness. These organisms live in a habitat that is shrinking. As the ice shelf thins and the grounding line retreats, the cavity beneath the ice expands. Light may reach areas that have been dark for millennia. The temperature changes. The current patterns shift. For organisms adapted to the most stable environment imaginable, even small changes can be catastrophic. Scientists are calling this the hidden frontier of Antarctic research. The cavities beneath ice shelves are one of the last truly unexplored environments on Earth, and they are changing before we can even document what is there. The race between discovery and destruction is not a metaphor in the Southern Ocean. It is literal. Every month that passes sees new species found and new habitats altered. The scientific community is simultaneously writing the encyclopedia of Antarctic life and watching the chapters being revised by forces beyond anyone's control. And above the ice, the atmosphere itself is changing in ways that feed back into the ocean. The Antarctic polar vortex, a band of strong winds high in the stratosphere that circles the continent each winter, has been strengthening and persisting longer into the spring months. This is linked to both the ozone hole, recovery and climate change, and it affects the surface winds that drive the ACC and control the sea ice extent. When the polar vortex is strong, the surface westerlies are pushed closer to Antarctica, concentrating their energy over a narrower band of ocean. This can enhance upwelling near the coast while reducing the wind-driven mixing farther north. The effects cascade through the entire system. More upwelling near the coast means more warm deep water reaching the continental shelf. Less mixing farther north means less nutrient delivery to the open ocean phytoplankton. The atmosphere and the ocean are locked in a dance. The ocean affects the atmosphere through heat exchange and evaporation. The atmosphere affects the ocean through wind stress and temperature, and both are being altered by human activity in ways that compound and amplify each other. There is a concept in complex systems theory called an attractor. An attractor is a state toward which a system naturally gravitates. Think of a ball in a bowl. The ball always rolls to the bottom of the bowl, no matter where you place it. The bottom of the bowl is the attractor. The Southern Ocean has had the same attractor for 34 million years. Cold water sinks, ice forms, the current flows, the conveyor belt turns. The system always returns to this state, even after perturbations. Ice ages come and go, but the fundamental operation of the Southern Ocean persists. What scientists are now asking, quietly and with increasing urgency, is whether we are pushing the system out of one attractor basin and into another. A new state, a different bowl, one where the water does not sink the same way, the ice does not form the same way, the current does not flow the same way. A state that no human civilization has ever experienced, because it has not existed for millions of years. The transition between attractors is not smooth, it is abrupt. The ball rolls along the rim of the first bowl, teetering, and then suddenly drops into the second. This is what tipping points mean in the context of the Southern Ocean, not gradual change, but a sudden reorganization of the entire system into a new configuration. We do not know where the rim is. We do not know how close we are to the edge. The models give ranges, probabilities, confidence intervals, but the Southern Ocean has already shown that it can surprise us, that it can change faster than models predict, that the thresholds may be closer than we thought. This uncertainty is not a reason for despair. It is a reason for urgency, because while we cannot be certain exactly when a tipping point will be crossed, we can be certain that every fraction of a degree of additional warming pushes us closer to the edge, and once we go over, there is no climbing back. The Southern Ocean has been telling us this for years, in its warming water, in its slowing currents, in its retreating ice, in its changing ecosystems, in the unprecedented events that have been documented with increasing frequency since the turn of the century. We did not listen for a long time. We did not even put this ocean on the map, but it is on the map now, and the data is coming in, and the story it tells is one of an ocean in transformation, a planetary system being pushed toward boundaries it has not approached in millions of years, and a window of opportunity that is still open but narrowing with every year that passes. There is still time, there is still ice, the current still flows, the water still sinks, the phytoplankton still bloom, the whales are coming back, the research vessels are out there in the roughest seas on Earth, gathering the data that will tell us what happens next. The Southern Ocean waited 68 years for us to acknowledge it. It has been infinitely more patient with us than we deserve, but patience is not the same as permanence, and the ocean that we were so wrong about for so long is now teaching us in real time what happens when you take the most important system on the planet for granted. The engine at the bottom of the world is still running. Listen to it while you fall asleep. It is the sound of the planet breathing. Sleep well. There is one last thing worth knowing before the night takes over. In December of 2023, a research team aboard the icebreaker RSV Nuina lowered a set of instruments through a hole in the sea ice off the coast of East Antarctica. They were measuring the temperature and salinity of the water column, a routine operation that oceanographers have been performing for decades. But the readings they got back were not routine. The deep water was warmer than any previous measurement at that location, not by a fraction of a degree, which would be significant enough, by a margin that exceeded the instrument's expected range of natural variability. The scientists recalibrated. They measured again. The reading held. The deep Southern Ocean, at that specific location, was warmer than it had ever been recorded, and the warmth was not confined to the surface or the intermediate layers. It extended all the way down to the abyss thousands of meters below the ice, in water that was supposed to be among the coldest on the planet. One measurement at one location does not define a trend. The scientists knew that. But it was consistent with everything else they had been seeing. The warming of the deep southern ocean is not a prediction anymore. It is an observation. It is happening now in real time, in water so far removed from the surface that it should take decades or centuries for atmospheric changes to reach it. The speed of the change is the message. We have built our civilization on the assumption of a stable climate, stable oceans, stable ice, stable coastlines, stable seasons. The Southern Ocean was the hidden machinery behind that stability, the thermostat, the buffer, the quiet engine running beneath everything, doing the work that kept the planet's systems in balance. And that engine is changing. Not in a future scenario, not in a worst-case model. Now, today, in the water beneath the ice, in the currents that circle the continent, in the density of the bottom water, in the health of the krill, in the breeding success of the penguins, in the thickness of the ice shelves, in the methane rising from the seafloor, in the species being discovered and threatened in the same breath. Every discovery we make about the Southern Ocean reinforces the same conclusion. We were wrong. Not about one thing, about many things, about the water, the ice, the life, the speed, the scale, the consequences. We underestimated this ocean in every dimension, its importance, its fragility, its connectedness to everything else. But the story of the Southern Ocean is not a story about doom. It is a story about discovery, about a species, our species, slowly waking up to the reality of the system that sustains us, about scientists risking their lives in the worst conditions on Earth to gather the data we need, about the gradual, painful, necessary process of updating our understanding of the world when the world tells us we got it wrong. The Southern Ocean has been telling us something for a very long time, in the language of temperature and salt and ice and current and carbon and life. We are finally starting to listen, and what we hear, if we are honest with ourselves, is both a warning and an invitation. A warning that the engine cannot run forever on the trajectory we have set, and an invitation to do what humans have always done when faced with a challenge we finally understand, to rise to it. But that is a story for the morning. For now the current still flows, the ice still glows blue in the polar twilight, the whales are singing somewhere in the deep, and the Southern Ocean, the last ocean, the forgotten ocean, the most important ocean on Earth, keeps turning. 34 million years and counting. Sleep well. And if you are still awake, here is one more thing to carry with you into sleep, somewhere beneath the Antarctic sea ice right now, in water that is barely above freezing, a tiny creature called a pteropod is building its shell. Pteropods are sea butterflies, snails that have evolved delicate translucent wings and swim through the water column like something from a fairy tale. Their shells are made of aragonite, a form of calcium carbonate that is particularly sensitive to ocean acidification. As the Southern Ocean absorbs more CO2, the water becomes more acidic, and as the acidity increases, it becomes harder for pteropods to build their shells. In some parts of the Southern Ocean, the water has already become corrosive enough to dissolve pteropod shells before the animals finish building them. They are literally dissolving alive, their protection eaten away by the chemistry of water that is absorbing too much of the gas we keep pumping into the sky. Pteropods are not charismatic megafauna. They do not make the news. Nobody puts a pteropod on a fundraising poster. But they are a vital link in the Southern Ocean food web. They are eaten by fish, by seabirds, by juvenile salmon, by whales. And their sinking shells, like the fecal pellets of krill and the bodies of dead phytoplankton, carry carbon to the deep ocean. They are part of the biological pump, part of the engine. When the pteropods go, the food web loses a link, the carbon pump loses a cog. The system becomes a little less efficient, a little less resilient, a little less capable of doing the work that the planet depends on it to do. They are small, they are fragile, they are beautiful, and they are disappearing. The Southern Ocean is full of stories like this. Small stories, quiet stories, stories that happen in the dark, in the cold, in the deep, far from anyone who might notice. Stories about organisms that have been doing their part for millions of years, cycling carbon, feeding predators, building the foundation of an ecosystem that supports everything above it. Those stories are changing now, and the changes are coming from us, so that is the Southern Ocean. The ocean that did not exist on our maps. The ocean that took 68 years to recognise. The ocean that absorbs our heat, buries our carbon, feeds our oxygen into the abyss, drives the currents that shape our weather, supports life forms that we are only just beginning to discover, and is now, after 34 million years of quiet service, sending signals that it cannot keep doing this forever. We were wrong about it. Profoundly, comprehensively, dangerously wrong. But we know more now than we did yesterday, and tomorrow we will know more still. The engine at the bottom of the world is still running. Listen, sleep well.